Okay, this circuit is our basic series RL circuit. The first thing we're asked to do is calculate the real reactive and apparent power for a circuit. Now, even though we're not asked to, typically we must start with a calculation of impedance and then current. And so we'll start off with the inductor. And for the inductor, the inductive reactance is equal to 2 pi times F times L. The frequency is given. It is 60 hertz. And so we have then 2 times pi times 60 hertz times the inductance value, 0.2 henries, gives us XL is equal to 75.4, and the unit for inductive reactance is ohms. Now, at this point, we could sketch the impedance triangle, I suppose. The impedance is given by Pythagoras' theorem, where Z is equal to the square root of R squared plus XL squared. And so we have the square root of 50 ohms squared plus 75.4 ohms squared, and we should come up with 90.5 ohms. Now that is the total impedance in the circuit. Remember, if we are going to apply Ohm's law to the circuit to calculate I is a circuit current, so therefore we must have the total impedance of the circuit before we can do the current calculation. Remember that the 100 volts of the source is an RMS value. It does not appear across the resistor. It does not appear across the inductor. It appears across the circuit. So circuit impedance is necessary to calculate the current. So the current in the circuit then will be equal to E divided by Z. We have 100 volts divided by an impedance of 90.5 ohms. The circuit current then will have a value 1.105 amps. Now that current goes through each component in the circuit. So we now have enough information to calculate the current, the power rather. Real power, P, is equal to I squared times R if we don't have voltage. This is the easiest way to calculate P. 1.105 amps squared multiplied by R, 50 ohms. That gives us P is equal to 61.05. The unit for real power, watts. Now, reactive power. And in this case, inductive reactive power, QL, is equal to I squared times XL. Again, if we don't have voltage, this is the easiest calculation to do. 1.105 amps squared multiplied by 75.4 ohms. And so we find that QL is equal to 92.1. The unit for reactive power, VARs, or volt amps reactive. So reactive power then at Q equals 92.1 VARs. Now, for the apparent power, more than one way, of course, to calculate the apparent power. And so remember, the apparent power, S, is equal to I times E. we have 1.105 amps multiplied by 100 volts, and that gives us S is equal to 110.5. The unit for apparent power, volt amps. Now, here, consider the fact that we should also be able to say S equals I squared times Z. S is equal to the square root of P squared plus QL squared. And we should be able to confirm approximately 110 volt amps with either of those calculations as well. Okay, the next part we are asked to calculate the phase angle. The phase angle can be found now from the information we have for impedance or the information we have for power. At any time here, it would perhaps be helpful to sketch the power and impedance triangles. However, we are asked for those last, and so I'll wait a minute before I calculate those. In any event, now for part B, the phase angle is theta, and theta is equal to the inverse tangent of the vertical component of impedance divided by the horizontal component of impedance. We could calculate then the inverse tangent of XL divided by R, or the inverse tangent of 75.4 over 50, and theta then becomes 56.5 degrees. We should specify that it is lagging phase angle because this is an inductive or lagging circuit. Now, in addition, remember that using the power components or the power triangle, theta is equal to the inverse tangent of the vertical power, or QL, over the horizontal power, P, and the inverse tangent then of 92.1 vars over 61.05 watts should also yield a theta of 56.5 degrees, and of course lagging. Now, the power factor then is generally given simply as cosine of theta. And so the cosine of 56.5 degrees gives us 0.552. And again, we should say that the power factor is lagging. In addition, remember that the power factor is defined as the ratio of P divided by S. And so 61.05 watts divided by 110.5 volt amps should give us a power factor of 0.552. Remember, we should always specify that that is lagging power factor. And the last part of this question then asks us to sketch the power and impedance triangles. And so if we start with the power triangle, we have P, QL, S. P equals 61.05 watts. QL is equal to 92.1 vars. Maybe I should have drawn it a little bit more to scale. S at 110.5 volt amps. And we should always include theta on the sketch, 56.5 degrees. Now, for the impedance triangle then, we have a similar triangle where we have R is equal to 50 ohms. XL is equal to 75.4 ohms. Z is equal to 90.5 ohms. We should indicate theta at 56.5 degrees, and this angle in the corner is a right angle. Now, it might be important to point out here that these triangles are considered lagging triangles. This is an inductive circuit. Inductive circuits are called or considered to be lagging circuits because the current lags the voltage in the inductive circuit. That means that the power factor lags, theta lags. We draw the triangles like this. We call them again lagging triangles.